Our speaker today is Erin Meger, and she will be talking about distance eternal domination on graphs. Erin has done a fantastic job with WinCom, and we're so delighted to have her present today.
Thank you so much, Sandra. And thank you so much to all of the organizers for thinking of me and for inviting me today. The CUNY Combo Seminar is always a pleasure to speak at. It's a fun little group. So yes, I work at Wilfrid Laurier and I also run WinCom. So if you have any questions today, please feel free to pop them in the chat or unmute yourself and let me know. And I'm happy to take any interruptions. There's also plenty of time for questions at the end. So today I'm going to be talking a bit about the idea of distanced eternal domination on graphs. So this is work that I did in my first postdoc at Mount Allison University with Emmy Messenger and Danielle Cox, and they're both out in the East Coast of Canada. And so this work builds on some of what I did in my master's, which was cops and robbers, and I've done a lot of work on games. So the last time I spoke in this seminar, I did a talk on network generation and complex networks, and this time we're doing some games, so something a little bit different. So let's go ahead and learn a bit more about what do we mean by eternal domination and what do we mean by adding in distance. So the idea here is that we have some sort of graph. And so what I've taken here is a map from my previous postdoc at UQAM. So this is the UQAM campus in downtown Montreal. And we have, say, we're building a network or a graph based on the map here. So we have all of our nodes are these stars, and say they're connected based on what roads are connected. So I want to introduce this notion of guarding. And so what we have here is, say, at some time, there's some attack. So say we have this attack right up over here and right at UQAM. So an attack occurs. Our idea with guarding is we want to be able to reach this vertex and guard the vertex in a very short amount of time. So this eternal domination idea says, I want to be able to move on to this vertex and vanquish the attacker, But because we're dealing with this in an eternal setting, what happens at the next time step is another vertex is then attacked. We then have to say, how can we move to still make sure that we land on this attacked vertex and guard the attacked vertex? Okay. So the idea here was the attack could happen anywhere, but because we had been up at one of the stars, we were able to quickly move to the other vertex because there was that nice edge that's in between there. However, we may have an attack that's very far away, and we might not be able to get to this vertex in just our single time step. You'll notice here, there are no edges between these two vertices, so we can't make this, we can't protect against this attack. So this is our general idea of eternal domination. So we want to dominate the graph in the sense that we can reach any vertex at any time, and we want to do so eternally. At every time step we move, but we have never moved out of place of a dominating set. So I'm going to do a little bit of a background on the idea of domination and the different styles of domination that have been studied in the literature. And we'll go through quite a bit of history there. We'll introduce a bit of this distance k-domination or eternal k-domination as we've called it. We'll talk a bit about our results and our main upper bound that we have for trees. And again, feel free to ask any questions at any time. So let's go ahead and go into the introduction. So we have some dominating set, and the idea of a dominating set is that any vertex not in the set is, or any vertex in the graph is either in the set or adjacent to the set. So in our guarding sense, we can move to that vertex in a single move, so across a single edge. And we have this idea of an eternal security set, and this is where things really began. So we have some set, and whenever we have this sequence of attacks, we are able to move one guard along a single edge in order to make sure that this we cover the attacked vertex. And furthermore, we can always make sure that we are then still able to do that in the next go around. So this was done by a big group So Berger, Kika, Meinhard, who also does WinCom with me, Van Uren, Winterbach, a few different people. It was also formalized by the head Tanemi and head Niemi and Godard a little while later, but the idea was really the same. So when we're dealing with this security idea, we have this limitation that only one of our vertices is moving at a time. And so there's this notation that was then created to do the infinite on the gamma, and gamma is our traditional domination number. And the infinity is showing that it happens indefinitely, and the 1 is to indicate that only one guard is moving. And our goal here is to determine these numbers of the graph, or the parameterized version of the game of the graph, which is, quite simply the minimum possible that we could use to make sure that this is a valid set. So again, just like the domination number is the minimum size of the dominating set, the eternal domination, or the internal security number, is the minimum, size of a set that has this property hold. So fairly straightforward. So again, the same group with Kika and I believe Gary was in there as well, is this. So we want to start bounding these different things. Oh, that infinity didn't generate. That's okay. So we have the independence number of a graph. So again, the largest possible set of nodes that do not have edges between them. And the clique number, we're going to use theta here, or the clique cover number. So again, a clique cover is just you find different cliques where they're each maximal with respect to each other, and then you find the minimal possible clique covering of the graph, and that's the clique cover number. We can also think of the clique cover number as the chromatic number of the dual, or of the complement, and that's my preferred way of thinking about it, but it's up to you. So the idea here is that we can bound this eternal security. Again, when we're doing this eternal security, we're only moving one guard at a time. And so we can bound this in between these two numbers. Unfortunately, these two numbers can be quite different. But a little later, we were able to, Gary and Chip, two people who traditionally, they're part of the group that works on these style of problems. They were able to come up with a slightly better bound by doing the independence number, +1 choose 2. So this bound was a little bit better, and this is a little bit smaller than the theta that we were looking at before, and is a bit more precise. We also get this double bound that only has to do with the independence number of the graph. So now we no longer have to worry about the clique number, which is a little bit more difficult to compute. So because they were able to take these two bounds that had to do with the independence number, we were able to then figure out how difficult these problems are to solve. And when we're only moving one guard, we have this nice property that because we can find the independence number of the graph in polynomial time, we can also find an upper bound for this number in polynomial time, which is great. So moving forward, we wanted to learn a little bit more about how can we relate these ideas of this eternal security number to other graph parameters, or even, other different particular settings. And so we've learned that the domination number is exactly the eternal security number. Again, we're doing it infinitely with one movement at a time. We know that these are always going to be the same value if and only if our domination number is exactly the clique cover number. And again, this is this is a bit of a straightforward upper bound, and the lower bound is a bit more work. So some examples is if we think about the powers of a graph, right? So if the power of a graph would take, say, any vertex, u and v, we're going to add the edge u and v whenever the distance between those vertices is at most k. So essentially, you look at all the possible paths, and so g to the k would have all of the edges of g, all of the edges of g, plus an edge between any vertex that's connected of path length up to k. So hopefully that's a more common thing that people are aware of. And so what we're able to do is whenever we take a cycle on n vertices, and then we take the kth power of it, we can see that these two values are in fact equal. And there's a few other vertices where this equality holds like this. But this is the best way to do it. And so you can get that nice circle with all of the different paths in between. So that was mostly focusing on the history of this with eternal security, which is again where this all started. But eternal domination came around by saying, well, what if we can move more than one different guard at a time? Which is something that definitely seems like a great thing to have happen. And it's a great generalization. So we now can define this instead of as sort of these sets and these minimizations over different sets. We're going to think about this as a graph process. So we'll start with some dominating set. And at each time step, we will attack a vertex, so flag it in some sort of way. The guards will then all shift in order to cover the attacked vertex. The new locations of these guards must themselves also be a dominating set. The benefit to eternal domination over eternal security is we now actually need fewer guards. In the past, whenever we moved a guard onto a vertex, we couldn't shift any of the other guards, which meant we needed to make sure that there was always a guard guarding every other guard, right? So whenever we moved someone, we would have to make sure the old position was still covered by a different guard. Whereas now, because everyone can shift, we have the luxury of being able to have one person move and all of the guards shift together, which provides a much more interesting and a lot more of a dynamic process along on this graph. So the way that we're going to denote the eternal domination number here is exactly the same way. So we get this gamma infinity, and this time we're going to use an all at the bottom to show that all of the different guards can move. And again, traditionally, this is the minimum size over all possible sets that satisfy these conditions. So this was studied mostly in this Niemi paper, and I believe this is the first time that this was introduced, but it may have been introduced concurrently also by Chip and Gary, so Klostermeyer and McGilvery. So again, the idea is, how do we look into these different papers or these different parameters based on other things we might know about the graph? And in general, these graph process and sort of gamified parameters tend to lean towards other graph structures and properties in order to learn a bit more, and pretty fun. Anyway, so now instead of having the bounds on the clique number, which again, when we're only moving one and we have to make sure that we keep enough guards guarding the old locations, we now have this this benefit that we can move everyone a little bit, which ends up removing that necessity of this theta bound. And instead we actually get a diameter bound, which is much nicer. So we can think instead about this sort of huge diameter across the graph and how do we move all of our guards along it. And again, if we think about placing our guards, at every other space along a path, right? Whenever we have to guard, move to cover an attack, sorry, I think my hands are too big. Whenever we move to cover attack, we can just shift them. So say they're on all the odd vertices, we can then shift all of the guards to be on all the even vertices in order to cover the attack, and so on and so forth. So we need a lot fewer guards, but we definitely need at least this diameter. And again, this proof for this lower bound here is precisely having them align on the odd number, the odd vertices along the diameter path, and then shifting to the even. So again, the question is, when would this be equal to the traditional domination number? A great question. So when do I not need to add cops or add guards? And this is sort of the really interesting part. And typically we want to figure out, when are these the same? So when can I have a dominating set that can just move throughout the graph and always remain a dominating set, which is very interesting. And it turns out it's for Cayley graphs, which I'm not really surprised about, and probably no one else should be either, when we think about sort of how much transitivity is occurring. The conjecture is that this would be for all vertex transitive graphs, but in fact, this is not true. And so Chip and Gary were able to actually find a counterexample to this proof in 2007. I'm not as familiar with what the actual, disproof of it is. but I know that it no longer works. Okay, so here is a big image. So what's happening here? So I've thrown out so far today quite a lot of terms. There's gamma, there's alpha, there's theta, there's the gamma infinity, gamma 1, gamma all of these different things that are happening. And so let's take a look and see how these all relate to each other, okay? And so we have sort of this pathway here where we have this gamma. And we're looking through this. This theta up here is, again, our clique cover number, and we know that that's going to be bigger than this gamma. So again, this is just a Haas diagram, and we have up to 2 gamma. The R here, the 2 different R's that we see are the a thing called Roman domination. And this was introduced again by Berger and all, and with Kika and Gary. And so those are a bit different. So our versions that we're looking at, again, sort of, we're dealing with this and trying to figure out where we belong in this entire thing. And there's a lot happening. And the idea that I wanted to share by giving you this image is not to say, oh, let's, talk about how all of these relate to each other. The idea is that as we're changing up these simple rules, we have these graph parameters interacting in a very strange way, right? This is not necessarily transitive. This is not linear. This is a very interesting grouping of how these 2 different parameters relate. And we see that some of them can't even relate to each other not at all, but the small variations in these rules and the way that we create these dominating sets provides a very deep and rich literature and understanding of sort of what is happening in these different graph structures. And I find this very interesting. So we're going to add to the cacophony of all of this and add a new parameter that we want to take a look at. So the last thing is I have one cool theorem for the eternal domination before we move into eternal k-domination. And the reason I want to present this in the eternal domination case is this is something that we'll build on a lot when we get into our eternal k-domination. So again, this is Klostermeyer and McGilvery, so Gary and Chip. Part of it is they've done quite a bit of work, but they also have a couple of survey papers on this material where they've either restated or re-explained previous work. So they do tend to get cited a lot, but there's a lot of different people working on this, again, with the head at Niemi, the Goddard, and Berger et al., Mindhart. There's a lot of different people. Okay, so the idea in this original work by Chip and Gary was that for a tree, the eternal domination number can be determined in linear time. Again, with a lot of these problems, we're looking at more the complexity of how difficult they are to solve, rather than necessarily understanding the structures that provide different results. They're both interesting problems, but the 2 of them are very closely related, because I may not necessarily want to say, oh, if I have this or I'm minor free of whatever. Minors are really hard to check. Right? It's almost more interesting if can I ask a computer to compute this value for me to then learn something different about the graph. So what happens here when we're looking at trying to understand whether or not this happens in linear time is these reductions. So when we're dealing with just trees, and again, trees are nice. When we had that path, right, we were able to switch from odd to even. How does this generalize when we go up to trees? And our idea here is that we want to take some reductions. And the way that we'll do these reductions is we'll either delete the leaves or we'll delete the leaves and their parent in some sort of well-defined way. So these 2 different reductions that we're going to do in these well-defined, either just all of the leaves, or we can delete the leaves and the parent as long as they meet some sort of condition. We can do these 2 deletions in a way that gives us this this updated eternal domination number where, we've at most changed it by 1. And in fact, some of them will either decrease it by precisely 1, which is great, which means that we can continue to delete. We'll be in either one of the options, and we're able to do this in linear time and count everything. There's a note I want to make here is that the idea of understanding the complexity of these different parameters is studied the most often in spy game. So whenever we're talking about these different graph parameters or processes, there's usually two camps. There's the theoretical camp and the computer science applied camp. And typically these problems are found on both sides and eventually they collide. And so one of the ways that these two areas have really collided is in the idea of spy game, which is a little bit more applied than I'm super familiar with. Although one of my academic siblings does work on this. But it's a lot more tied into how do we create different situations and games and graph processes that have this different amount of complexity to them in different settings, and some of them relate and some of them don't. But it is interesting. If you're into the complexity stuff, I highly recommend you check out Spy Game. A lot of this stuff is a lot more either structural or case-based or theoretical in general. So again, this only works when we have these trees and we can apply these reductions, which we can always do. But in general, this game is actually really, really, really hard. There's only a few cases where we have really low complexity. So with all of that aside, I want to now introduce eternal k-domination. So before we get into our current new description, are there any questions about any of the literature, sort of the setting that we're in? Doesn't look so. All right. Let's move into our new parameter, this eternal k-domination. Okay, so again, here is our setup from earlier. Again, we have Montreal. And paying homage to one of my other postdocs. And remember in our first example, we had that attack right at the top, and the guard was able to move to it and move to the next attack, which was just underneath. West, in fact, if you are in Montreal. So especially here in New York, it's always nice to chat because Montreal orients their streets in the other way when they curve. So north is actually, you know, to the side here, which is always cute. So anyway, I digress. So this new attack that we're having at this red vertex right at the bottom, and hopefully for those of you who maybe have difficulty seeing colors, that's this one. This one up here is green. The others are all blue. So when we had this attack in the past, we were not able to reach it. So the way that we decided to come up with this eternal, you know, distance domination is sometimes we might have this opportunity where we don't need to reach every attack instantly, right? We can take some time. So the idea is there is an attack and the guards now have up to k time steps to be able to move towards the attack. This is quite interesting. So now all of a sudden, instead of having this vertex be too far out of reach, we are now able to reach this vertex in say 2 steps. So let's be a bit more precise as we define this. So we have a graph. We're going to say that a distance k dominating set, again, has the property that all of the vertices in the graph are either in the set or have a distance to the set of length at most k. And again, we use the inclusive definition of k here. The minimum size over all of these sets, again, we always minimize, is gamma to the power of k. In some literature, you might see that a distance k domination, maybe gamma with a subscript of k. We're going to be using an exponent of k because all of our other parameters go in the subscript, and we already have, you know, infinity all, and it's a lot. So we're putting this in the top. So our goal here is that we want to define this analogous game to this eternal domination side where we're able to do this sort of slower movement or distanced movement. So the guards will be allowed to move up to k edges, so anywhere along the graph up to that distance of k after any one attack. And the attack does stay in place. So essentially a vertex is being flagged and we're moving towards that flagged vertex. The other thing is we will allow all of the guards to move simultaneously. For one, if we think about this in terms of what application, maybe we're guarding a museum or something like that, it doesn't make sense to sort of have one person, kind of go off, check something out and come back, right? We want them all to be moving simultaneously. And that allows us to sort of keep more of the graph guarded by letting them all move together. So we're going to get a little rigorous. We've been a little hand wavy. So let's be really precise about how we are actually moving these guards and dealing with these attacks. So for two different dominating sets, we're going to say that one of them transforms into a different dominating set whenever there exists some vertex in one of the dominating sets. In the other dominating set, there is a vertex that has this vertex in its neighborhood. And that can be true for every single vertex in the dominating set. The other thing is it is this closed neighborhood, so it could be the same vertex itself. So the idea is that whoever is guarding on vertex 1 is able to either exist on vertex 1 or move to U1. Okay. So the idea is this is a move for the guards. Again, I just want to make a notation here is that this kth neighborhood is denoted with this nk. So again, we say that these two sets transform if for each vertex in the secondary set, it is either the vertex in the first set or it is in the neighborhood. And we do want to make sure that these are staying consistent. So we want to make sure that UI and VI are going together. We don't want to have, there could be some issues with the set where maybe, two of the vertices have to go to the same place, but we're indexing them in such a way that we want to make sure that UI and VI correspond. Okay. So the idea is that this is a permissible move for the guards. From there, we can create this idea of an eternal dominating family or an eternal k-dominating family since we're dealing with k-domination. So this is going to be a set of these dominating sets, right? So it's a set of sets of some size, say Q. And every single dominating set for any vertex in the graph, if we have an attack, we can then find a different dominating set in this set and transform into it. So essentially what we've done, instead of thinking about this from a graph perspective and thinking about the movement or the edges or how close different vertices are to each other, we're thinking about these as sets of sets. And do these different sets have these sort of overlaps and properties that we're looking for? So again, this dominating family, we exist in some game state. There exists an attack, and I say I would like to exchange one of my guards for a different guard. There exists that dominating set where we can transform into it, where we have now covered that vertex, and we can move on. Any element of this family is always going to be an eternal k-dominating set. And the other thing to keep in mind is that all of these dominating sets must have the same size. We have to make sure that they have the same size or else they wouldn't be this family. Now it is fine for two guards to occupy the same vertex, but the dominating set is still technically the same size, but allowing for repetition. Give or take. In fact, it is never useful for a guard to occupy the same space. So we can say that they don't occupy the same space, or we can say that they can, but they don't. Okay. So this is our game setup at this point. Again, the next thing that we're going to do is find the eternal k-domination number of the graph by minimizing over all possible dominating families. Okay. So any question about the game that we are working on? All right, so we're going to spend the last 20 minutes here talking about a bit of our results and learning a bit more about this game and how it works in practice. We're going to talk a bit more about some structural results that we found, what different structures lead to reduced or increased eternal k-domination numbers. We'll talk a little bit about the complexity results, and we'll relate this new parameter to some other well-known graph parameters. So, and we also have a result on trees that builds on that initial result from McGilvery and m-ary that we talked about at the beginning. So let's go ahead and get into some of these results. So the very first thing that we looked at is we absolutely need to make sure that we have a k-dominating set. That's nice and easy. But the thing that was very interesting is that we also have this luxury that if we have a dominating set of half the size, right, the idea is that the guards would be able to go and come back, right? So they could move and return to their initial position. And so we have this really nice upper bound for that, because every guard would be able to move and then return to that, to cover that first position, because they're able to move this distance. The next thing that I want to talk about is the relationship between these powers of the graph that we brought up earlier and this eternal k-domination number. So just right from the get-go, just from the definition itself of having these different edges, we are able to say that the eternal domination number for the kth power of the graph is exactly equivalent to the k-domination. Now, while this is great, computing powers of graphs isn't necessarily the easiest thing in the world, and computing roots of graphs is even harder. So while this is nice, we get the following result. For any graph, deciding if a set is itself an eternal k-dominating set is in x time. So this is really interesting. So this is incredibly difficult. And the reason why is precisely because it is difficult to compute the powers of the graph. So again, we want to take a look at sort of what the classic things are to do. So if any of you have seen some cops and robbers stuff or done some other game stuff, you know the very first thing you do is you check cycles, paths, and complete graphs. Sometimes you go for a wheel, sometimes you go for products of paths. Depends on your flavor of the day. So we started with cycles and paths. So again, this comes out of this idea from this had m-ary research, right, with the diameter bound. So when we have these paths, let's think about what's really occurring. We have this selection of these guards correctly placed in this dominating set along this path. And in the original game, we only had to move one position. We could move from evens to odds or odds to evens to make sure that we covered the entire graph. Here we have a much larger area that we can cover. We can cover up to this k. And the idea here is that when we're in this path, we can sort of slide ourselves to one side or slide ourselves back, right? We need to be careful when we're dealing with those leaves, though, is we can never be too far from the leaf, because we always need to be able to get back to the leaf, and we always need to be able to leave the leaf and come back forward, but not too far. So we end up with this, bound here where we have that the domination number for the k distance, not eternally, just one time. We get this nicer bound where we get to spread the guards out along this, every, 2k vertices. But when we're dealing with this eternal version, we don't get that luxury because we have that shortened section on those paths. And we need to be able to make sure that whenever we send a guard in one way, we can also make sure that we can send them back. So the guards now, instead of being able to guard 2k in each direction, as was the case with just the regular domination number, we now have to make sure that each guard guards a total of 2k. So k on one side and k, or I guess just the k on either side, the total of k on both sides. So the idea is you have that guard every k. So if you move one way, you can also make sure that you can get back to that original position. So the idea here and the way that we proved this was just whenever you had to send another guard in from a previous subpath, you had to make sure that they could also go backwards. The cycles, however, were much nicer. So what's nice about the cycles is that we were able to show that the eternal domination is exactly equal to the k-domination in this case. And this should make sense. Again, we're on that cycle. We don't have the problem with those endpoints. We can just simply shift all of the guards. And it does work exactly as you expect, which is fantastic. So let's see this in action. When we're dealing with the cycles, again, we place the guards in this K dominating set, which again, we know is difficult to find, but it's a cycle. It's not too bad. It can be every 2K vertices. Every vertex is going to be then within K from any one guard. So again, when we say that it's this 2K setup, right? We have some guard here and 1K in this direction, 1K in this direction. It covers, 2K, but it also covers itself. So it ends up with this 2K plus 1. So at each attack, all of the guards would move together. And because we're on this cycle, that guard from the guards all shift. And so even that guard that moves to go reach that attack, they can all shift back around and cover where that last cop had moved off of, or the last guard. So I do have the space here in order to draw this picture, but I have been having trouble with my tablet, so we're going to skip that today, unfortunately. But again, hopefully I talk with my hands enough so this is clear. On the path, again, let's be really clear about this. So when we're dealing with the path, we have these two endpoints. And so, if we have every guard is within K, it's straightforward again, because we have sort of the guard exists here. We have K over 2 on this side, K over 2 on the other side. And the guard can just sort of move between this path. So the guard has this set path of size K plus 1 that it guards. And at no point does the guard ever have to leave its set, because whenever it's at the farthest endpoint of its subpath, it can always reach the other farthest path of its subpath, okay? The trouble, though, is when we have to move, right? So how do we show that this, when I do it with the 2K, that it's going to be insufficient? Because again, think about what we did for the cycles. We had, K on one side, K on the other side. Why can I not move to that K distance and then have someone else come in and cover this? And we'll see why in a moment. So if we take each subpath of like K plus 1, right? And if we have only this many guards, so the N over 2K plus 1, there's going to be some of them that doesn't have a guard in it on every time step. So we'll call it PJ. So let's think about what has to happen if there's an attack in this subpath of length K plus 1 that does not have a guard on it in some time step. So no guard from anything before it would be available. If a guard was available, this would not be the lowest index where it is not guarded at all times, okay? Or does not contain a guard, okay? We want to show that it's not guarded, but it doesn't contain a guard. Again, we are dissecting this path into these K plus 1 sections. So no cop from the previous can come in because all of those paths need to have the guard on it at all times. This path up here would then need to send in a guard to protect that vertex, okay? And say we can do that, there's enough space, it all works out, from this thing. However, now this path is the lowest index that doesn't have a guard on it at that particular time step. Everybody else does. So it needs a guard that comes in. And as we keep going and sending these guards backwards, at some point we get to the leaf, and the leaf wouldn't be guarded because that cop had to move, or that guard had to move backwards into the previous. We had no guard then to move forward once it moved backwards because it left that path of PK plus 1 and it's just too far for it to move. So that's our idea here with the paths. So what's nice here is we have shown that there is a difference and is a gap between the distance domination and the distance eternal domination. And there are graphs where it is equal and are graphs where it is not equal, which is great. So let's take a little bit then to think about how can we generalize these results for paths and cycles into other types of graphs. Hamiltonian graphs were a great place to start because we had this really nice result on cycles. So if the graph is Hamiltonian, we have a cycle that goes through all the vertices. We can simply stick all of the guards on the Hamilton cycle and move them around as we need. And this is a great result because the attacks aren't moving, they're stationary, only the guards are moving. The guards can simply ignore the edges that aren't in the Hamilton cycle, which is so then the question becomes, if we can just ignore these edges, what else can we do? If we can reduce a Hamiltonian graph to just its cycle? What else could we do? Can trees come in and give us a boost on this? And in fact, they can. So because we can remove any edge in the graph by just ignoring it, we say, oh, yes, it was in the neighborhood, but we just restrict it. Essentially, all we're doing is restricting the possibilities for the different eternal domination families. So, right, when we defined that, we had, it was a given set, maybe Q, and it was all the different transformations we could have. What we've done is we've said, okay, well, any transformation that said, this particular U and this particular V were adjacent, we ignore, we throw out a bunch of eternal dominating families. And because we're throwing out eternal dominating families, we can only increase our minimum dominating set. So we end up with this really nice bound, is that whenever we have a spanning tree or any spanning subgraph, the spanning subgraph's eternal k-domination number is always going to be at least the eternal dominating number for the previous graph. Okay. We can't create any shortcuts or any new dominating sets. So our goal here is to solve this problem on trees, and we have about 5 minutes, so we'll see how far we can get. Maybe we'll take 6 or 7. So if we can get it for trees, we're a little bit closer to getting it for graphs. If we can show that it's really hard on trees, it might give us a little bit of a boost to show that it's really hard on graphs. So let's take a look. So our result for trees, it's our most important one. Can we find a reduction algorithm that is similar to that Klostermaier-McGilvery algorithm, which makes sense? How can we start to consider this idea of peeling back different parts of the graphs, considering them guarded and dealt with, and sort of dealing with an induction? Can we do it? Great question. We can. So let's define our 2 reductions. So we have some tree and some edge xy. We're going to say that this tx is the component of the tree. We remove that edge that we had, this xy. And that part that contains the vertex x, who cares if it's the top or the bottom, it doesn't really matter. Whichever part that was, we take that subtree as our tree. Because again, edge deletion disconnects the trees. So our idea here for our first reduction is we can reduce the graph if every single leaf in this tx component is within a distance k of that vertex x. So that means that if there exists a guard on vertex x, all of the leaves can be covered. However, we also require that the diameter of this graph is 2k. Okay. The reason for this is that if, say, one of the guards goes off to one of the leaves that's at distance k, we know that that leaf, that some leaf is now distance 2k. So if we were to move to that, particular leaf that had this big diameter, we would be in trouble. We wouldn't be able to get there. So what we need is we will need an additional guard on x. So we'll need 2 guards on x in order to then move from one to the other. So one will be in the leaf, one will be on the root, and they can swap back and forth, which adds an additional guard to the count. Okay, so we're able to now decrease our main tree by 1 because we know that there has to be that guard that goes off to help over there. Okay. So our second reduction is just a path with some of them being pendant edges. And again, this is a path of length k. And the idea here is that our diameter is significantly shorter. Okay. But here's the difference. And so when we say with maybe some pendant edges, what we're really saying is that it is every leaf is within distance k, but our diameter is precisely k. And so the idea here is that whenever we have our diameter being precisely k or precisely 2k, we know exactly how many guards that we need, right? We need 1 or we need 2. And so we can make these reductions. However, when our diameter for these subtrees is anywhere in between, we have absolutely no idea what happens. Do we need 1 extra guard or do we need 2? Who knows? And that's a great question. But with these reductions alone, we're able to then say some things about the trees, okay? So for every diameter in between these two, there exists a construction that increases the eternal k-domination number, and there is another one where it stays the same. And so this was our big breakthrough, was what happens in between anything. We have constructions that show that whenever we have these subtrees, we can build a tree that has these different properties, and we can't necessarily restrict or make any sort of reductions or bounds on our eternal k-domination number in general for the main tree. Okay, so what do those look like? Well, if one of them is, say a path, and there's the two endpoints are both k/2 from x. And if I remove those two endpoints, it doesn't or I remove x and it doesn't disconnect the remaining tree, or sorry, I remove the endpoints, it doesn't disconnect the rest of the graph. We end up with this, where it stays the same. And what happens for it to increase? This is a bit more complicated, so I think I'll leave it. I won't leave it here. So we have this path, the center is x, we have two leaves that are this, their distance is exactly 2k, and everything else in the graph, whenever we delete any of these vertices, we end up with these subpaths that are not too long. We don't have to decrease our domination number. And that's where things really get difficult. And again, this epsilon here is just this eccentricity of the vertex, so how far anyone else is away. So there are some cool pictures. So if we want to look at the pictures, we could do this. You can definitely pause the video if you are watching the recording, or you can look up the slides on my website, which I think are posted. But we do need a lot more structure in order to sort of understand what's happening when our subtrees have these, middle of the road diameters. So I'm going to leave this here. I'm going to skip the m-ary stuff, and we're just going to go into some open problems that are left. Well, there is a lot of material here. Open questions. So what do we want to learn about open questions? Can we describe different classes of graphs where we know that they're still equal? This is wide open. We have no idea. Are there any specific classes where we know that we can compute this really efficiently? So trees weren't it. And then maybe the reductions that we have aren't the right reductions. Maybe we need to find a different set of reductions that will help us understand how we can increase or decrease the eternal k-domination number in some sort of way that maybe leads us to a complexity result, or reveals something interesting about the nature of trees, or the graphs that have these different eternal k-dominating numbers. Now, we do have another structure that we can use, and there is one case that's missing, but we do have a bit of a better result here than what I'm giving in the talk, just because the one in the paper, it gets a little bit messy, if you will. So anyway, I'm going to go ahead and I will leave this here. Are there any questions or anything for me? I guess, Sandra, you'll probably thank me before we get into questions.
Let's thank the speaker. And I guess we're ready for questions.
Thank you.
Maybe I can ask one.
Okay.
So it's not known right now whether gamma, let's see, infinity k all can be computed efficiently for trees.
No. We suspect it won't be. I mean, we do have that for any graph, it is, very difficult to compute because of that result we have with the power graph. But for trees right now, we don't have enough information to say how difficult it is, unless you have these very, very particular cases. And there's a few cases, but just for trees, we don't know.
Are there any questions, or should we thank the speaker again? All right, let's thank the speaker.
Thank you so much.
And we'll stop the recording and then just chat.